Right, good evening everybody, just waiting for everybody to log on. The numbers are climbing now, so we'll just give it a few minutes for everybody to log in, and then we can start. Okay, apologies to those who thought it was starting at 6, but we were under the impression it was 6:30, 6:30 start, and we are still logging people in. So, right, we're a couple of minutes after start time, so we'll make a start. Well, good evening, everybody. From Essex IET local network, and this evening we have Andrew Herbert talking about Edsac, the first programmable computer that's currently being reconstructed at the National Museum of Computing near Bletchley. So over to Andrew to start the talk.
Okay, so hopefully people can hear me, and I'll bring up my slides if I can grab share screen. Hopefully everyone can see my presentation on the screen. So I'm Andrew Herbert. I'm wearing two hats for the purposes of this talk. I'm Chairman of Trustees for the National Museum of Computing at Bletchley Park, where we have the world's largest public accessible collection of working computers, going back to wartime code breaking machines through to the most modern microprocessors. The second hat I'm wearing is as the manager of the Edsac replica, which is into a build, and we're nearly there now.
Oops.
Doing arithmetic or whatever with a hand calculator or on a machine. And so the name they gave to their computer at Cambridge, Edsac, stood for Electronic Delay Storage Automatic Calculator. And that kind of also summarizes the architecture of the machine. It was an automatic calculator intended to do arithmetic work, and it used a kind of storage based on delay lines, and it was electronic, and all those things were quite novel in 1949. So that's a picture of the machine as it looked in 1949, 50, 51, in the kind of first phase of the life of the machine. And it provided a computing service to the whole University of Cambridge. Now, everyone who's involved with early computers likes to claim that theirs is the first in some way or other. And indeed, we all pick the set of adjectives that make ours the particular first. The claim really to having the first working computer that will be recognized as such by a modern computer engineer and programmer goes to Manchester University. They built something called the Small Scale Experimental Machine, nicknamed Baby, and their machine was working in 1948. But that was built really as a test rig to explore a new kind of storage technology based on persistent dots in a cathode ray tube. And the baby wasn't capable of solving useful problems. It could run programs, but the instruction repertoire was not wide enough, big enough to solve realistic problems. The Cambridge machine worked, so the 6th of May 1949 was the date it started running. And it was the first practical machine in the sense that people could use it to solve realistic problems. And indeed, it was built in the university, in a part of the university called the Mathematical Laboratory, to provide a computing service. The history of the Mathematical Laboratory, it was created just before the Second World War. And essentially, it provided a sort of library of calculating devices, which obviously in 1938-39 were all mechanical, and a small staff who could help people solve numerical computing problems, maybe aided by using some of those mechanical devices. After the Second World War, when the maths lab reopened, the founder came back from wartime work on radar and got to hear about some early developments in electronic computing and decided to build the machine. So the first claim for Edsac is so the first practical general purpose stored program electronic digital computer. It is entirely electronic. It does execute programs in its memory, and you can change those programs and load new programs without having to rewire anything or make changes. It's not the biggest or the fastest of the earlier machines, but perhaps the importance of it is actually that the whole concept of software really was invented by Edsac. A lot of computer pioneers were so focused on building their machines and getting them working, they didn't really think about how they might be used or what might make using them easier. Whereas the Cambridge crew developed a software system based on an extensive library of pre-cooked subroutines for things like mathematical functions, reading in data, printing out data, and a rather clever system so that you could build your program by combining those library routines with your own code, which you could write in a fairly symbolic form. You didn't have to understand the machine code and the binary, and you'd feed in your tape and the library routines it needed, and the Edsac would automatically glue them together and run your program. So that's an important part of the story. We shan't talk much about that tonight, but maybe if you want me to come back on another occasion, there's a whole lecture on that as well. The third important achievement of Edsac was the machine architecture and implementation was copied by Lions, the catering company, to build a machine they called Leo for Lions Electronic Office. And that was the world's first business computer. And they had the vision to apply computers to tasks like managing their payroll, managing their inventory, managing the scheduling. And indeed, they had to do so to maintain the economics of their business and reduce a lot of the people costs from the hand methods that they were using hitherto. In the Cambridge context, the most important thing about the Edsac was the way in which it transformed how science was done in Cambridge. It allowed people to work with, for the time, large amounts of data and undertake calculations that would previously have been impossible, to use numerical techniques where analytical techniques maybe fall down or couldn't scale or didn't exist. And as a sort of rough rule of thumb, Edsac ran at about 600, 650 instructions a second. That made it about 1,500 times faster than a postdoc or a PhD student with a hand calculator. And of course, it could run for more hours than a student would do. And that's probably actually the biggest speed up we've had between one generation of computing and another. We get very excited these days by Moore's law and the speed up that we've had year on year. But in terms of a single step, Edsac was quite dramatic. And it led to 3 Nobel Prizes in Cambridge. And they're all in areas that would interest members of the IET. In radio astronomy, Martin Ryle and Anthony Hewish came up with the idea of, rather than building bigger and bigger dishes, fill a field outside Cambridge with a lot of small antennas, collect the signals at each of them, and then numerically process them so that that field of small antennas essentially corresponded to a larger disk than they could afford to build. That work was very successful. And in their Nobel acceptance speech, they mentioned Edsac as if it was a scientist on the team, and explained that without the computing power of Edsac, they would not have been able to process the data to arrive at the results that they wanted. So that's in the field of radio astronomy. In the field of biochemistry, John Kendrew and Max Perutz used Edsac to do the analysis of X-ray crystallography of complex proteins. The structure of hemoglobin, I think, was one of the first results. And of course, that was an important part of the journey towards later unpicking the structure of DNA. And again, it was the ability of Edsac to process large amounts of data and to do large-scale calculations that made that possible. And indeed, there was a time in the early history of Edsac and its successors where most of the Cambridge X-ray crystallographers lived in the maths lab rather than in physics, because they spent more time on the computer than on the instruments. And then the third group was Huxley, Hodgkin, and Eccles, who used Edsac to model and understand the signaling that goes on in the human nervous system, and how information is communicated around in that network. And again, all 3 of these prize winners in their Nobel acceptance speeches mention Edsac as critical to their work. So let's talk a bit about the original machine and how it was developed. The man behind it was this character, M.V. Wilkes. Sadly, he died 12 years ago. He came to St. John's College in Cambridge to study mathematics. He was actually an enthusiastic radio ham, and for his PhD, he decided to move to physics and worked in the Cavendish lab under Rutherford. And his particular interest in physics was bouncing radio waves off the ionosphere. And because of that, when the Second World War came along, he was encouraged to get involved in the early work on radar. And he led a lot of the efforts on maritime radar. The first successes from people like Watson Watt were with airborne radar, which we know about from the stories of how the Battle of Britain was won by being able to vector the fighters to the right places. In parallel, there was a lot of development using radar, particularly to help ships hunt submarines, and that also was very successful. After the war, he came back to Cambridge and became director of the mathematical laboratory. The previous director had gone off to Oxford to be head of chemistry. And he got to hear of a document called Draft Report on the EDVAC by an American called John van Neumann. Van Neumann was part of the team that had worked on an American machine called ENIAC, which was an electronic calculator, but it wasn't really a computer in the modern sense. You had to wire it up to solve problems. And every time you wanted to solve a different problem, then you'd lose the machine for a day while the engineers reconfigured it. But from that experience, von Neumann had the concept of the stored program computer, and that's what he wrote up in the EDVAC report, and then proposed a design for building really quite a large machine. And in that report, he nails most of the ideas that are the basis of modern computer architecture, of instructions and memory and data, how the machine might work. Wilkes got to read that report and thought that Cambridge clearly needs a machine like that. He had the opportunity to go to a conference at Princeton University where all the American pioneers were meeting and discussing their ideas. He arrived late, as ever. It took a while to get funding organized, but it wasn't too bad because the Americans have been a bit hesitant to talk about the electronics and their computers. By then, the Cold War issues and so forth, people were starting to be secretive. So most of the conference had been spent on numerical methods, which Wilkes didn't really want to concern about. But by the time he got there, the audience rebelled and insisted that von Neumann and the others talk about their experiences. And he learned a lot from that. He came back from the conference on the Queen Mary and sketched out the design of the Edsac machine. And you can see where he stole the name from on the journey home. So there's Edsac in 1949. It's 3 rows of racks. You can just see the 3rd row at the back, built in what had been the anatomy school of the university. 3,000 hulls, and built over a period of about 3 years by a team of 10 or so engineers, most of whom were either people who worked with Wilkes on radar during the war, or instrument makers from some of the local companies in Cambridge, like Pi and Cambridge Instruments and so forth. So this is the floor plan of the machine. The memory, we'll talk about that in detail in a few moments, is mercury delay lines. These are tubes filled with mercury. They're held in wooden boxes, and they were divided into 2 sets that together gave you 1,024 words of memory. So there was a set of tanks at the back of the machine. The rear row had 5 racks in it. 3 of the racks were the arithmetic unit, which Wilkes and his colleagues actually called the computer, because in their mind it was the bit that computed. And the computer at its heart knows how to add, it knows how to collate, do logical and it knows how to complement, i.e. negate a number. And out of that, or out of those primitives, on top of that, you get subtraction and multiplication. There isn't a divide in Edsac, that's provided by software. The middle row is called control. That's what we think of as the central processor today. That's the part that knows how to fetch instructions, decode them, instruct the arithmetic unit to carry out the relevant calculation, and manages the transfer of instructions to and from the store, and the transfer of operands to the instructions, again, to and from the store. It's probably the most complicated part of the machine. In the front row, there are 2 racks. One called the pulse generator is essentially the central clock, and from that are derived the pulses that time the digits in the machine, and obviously various parts of the control of the arithmetic system are activated at different points in the sequence of pulses of data as it goes through the machine, and the input-output. You'll have noticed I've ignored 2 racks in the back and 2 racks in the front called store. Those held electronics that ran the recirculation system for the memory. And again, I'll talk about that in a moment. So that was the physical layout. There was a paper tape reader to read in your programs and data, a teleprinter to capture your output, and a set of cathode ray tubes that let you peek in at some of the registers in the machine and peek at the store. That was mainly intended to help the engineers with debugging hardware faults, but also could be of use to programmers if they want to know what was going on. There was a motor generator on the floor beneath, because in those days, the electrical supply in Cambridge, I think there were 2 or 3 suppliers, but none of them was reliable. So essentially the maths lab took a supply from each of them and used whichever was available to run the motor generator to give Edsac the current it needs. And Edsac takes about 9 kilowatts of electric power. It's quite thirsty. It gets quite warm in the summer. The logical block diagram is on the right. There's the store. Input reads from the input device and puts the data in the store, where it can later be fetched for calculation. Output takes data from the store and puts it on the teleprinter. Control orchestrates the overall process. And in the arithmetic unit, the key part of that is a register called the accumulator, which is where the results of calculations are stored. And obviously you can write the accumulator into the store, and as you're doing arithmetic, you can fetch operands, compute on them, and the results end up in the accumulator. So that's the broad structure. If I come down a level deeper in the architecture, it's a very simple structure. For each of the major units, for example, the arithmetic unit, down near the bottom of the slide, there's an input gate and an output gate. And so the function of main control is essentially to open and shut the input and output gates in the right sequence to make things happen. So if it's executing an order that wants to read an operand and then add it to the accumulator, it will open the output gate on the storage, on the relevant storage unit for the data to come through. It goes through something called the transfer unit off the output bus through the transfer unit onto the input bus, is gated into the arithmetic unit, where the arithmetic is carried out with the accumulator, and then the result as it's produced is gated out, and that can go, if there's a result produced, that is, that's gated out, and that can go through the transfer unit again and be gated into one of the storage units if the instruction produces a result to go into the memory. The job of the transfer unit essentially is to provide sufficient separation that results coming in are re-timed to line up with the recirculation of data in storage units. And essentially the machine is computing in the arithmetic unit on 1 bit at a time. So it's a serial processor. And that was a limitation on how big a machine you could build physically with the number of valves available and the current you could consume. Down at the bottom is a reflection of control. Control has its own register called the sequence control tank. That's what we'd call a program counter today. That fetches from the memory and gates the fetched instruction in something called the order tank. They called them orders rather than instructions. And then the order is decoded to understand what functions you want the arithmetic unit to carry out. So a fairly simple architecture. And although they called them input and output buses, actually both buses are effectively a wired OR distributed across all the racks in the machine. It's not a bus in the modern sense with consistent standards about voltage levels and timing and so forth. It is literally a wire. We need to talk a bit about computer memory. In 1949, it was too expensive to build an electronic memory. To build a set reset style flip-flop, you need about 5 vowels. You can tell I wrote these slides for an American audience. You need about 5 vowels per bit, and the machine has 17-bit words and a maximum capacity of 1024. So that will be 79,000 vacuum vowels. That's thermonic vowels. That's clearly infeasible. So all the early computing pioneers had to look to some other sort of technology. Wilkes picked up acoustic delay lines because he'd used those in radar. Manchester, as I mentioned, were working on using a cathode ray tube. The idea there was on one scan of the tube, you could write dots on the screen. You could then do a second scan to read the dots back. And then based on that, you could keep scanning the tube and rewriting the data if you wanted it to persist, or you could change the data if you had a new value. Or the other alternative was rotating magnetic drums. So with all these media as memory devices, they were complex, they themselves were expensive, not particularly fast, and often had reliability issues, and they all limited the speed of the computer. So all those early machines, essentially they ran at the speed of the memory. The electronics was capable of operating much faster, but waiting for the memory was always the Achilles heel. So these are the delay lines that Edsac used. They were built in batteries of 16, and each tube was filled with mercury. There was a piezoelectric crystal at each end, and essentially data was stored in the tube by pinging modulated RF signals through the mercury. The pulses traveled down the tube and then would be detected by the receiving crystal. That would then go into a piece of electronics that would clean up the signals, which were quite attenuated by then and had picked up noise, would clean up the signals and re-inject them. And there were 16 36-bit words circulating through the store, or you can think of that as 32 18-bit words, and the 18-bit hardware word held the 17-bit data word that the programmer could see. And the first bit essentially functioned as a spacer between consecutive words in the physical store, so that things didn't collide with each other. That was quite a difficult technology to make. The steel tubes had to be very carefully bored to minimize echoes. They had to be kept scrupulously cleaned. And indeed, about every 2 years, the system had to be drained down and the mercury redistilled as it corroded some of the metal and the various shims and gaskets and so forth used to hold it together. But it was a technology that worked. It came from radar. A friend of Wilkes's called Tommy Gold designed and built the delay lines for him. And in radar, the delay lines were used to remove clutter from images. Basically, you stored the previous scan in the tube, and then you subtracted it from the picture on the next scan. And what you were left with on the scan were things that are moved. And generally in military radar, that's what's interesting to you. So that's the memory medium. And the bit time traveling through the mercury is about 2 microseconds. And so you've got 18 bits in a word. You've got 32 words in a tube. So that's about 576 bits. So you're looking in the order of a millisecond or so to wait for data that's just been inserted in the tube to come out the other end. And again, that limits the speed of the machine itself. So let's talk a bit about building the replica. First challenge is authenticity. We don't have the original circuit diagrams or mechanical drawings. What we have are a lot of contemporary photographs and descriptions of the machine by people who used it and people who visited Cambridge, and accounts in various technical journals about particular bits of the machine the designers were proud of. So our aim is to be completely consistent with those photographs and records. Where we have evidence, we follow it. Where we can, we use period components and circuits when they're available to us. Where we have decided to vary is to use functionally equivalent modern components, particularly for resistors and capacitors. There are many people, men in sheds, who give us boxes of very old resistors and capacitors, but typically they're way out of tolerance after many years. And so while we are using period valves that we can get as new old stocks, and we are absolutely mirroring the period circuits when we can find descriptions of them. So for the passive components, we've allowed ourselves the luxury of using modern ones. But other things like coils and so forth, if we can't get them, then we try and manufacture exact equivalents to the historical ones. And as we've gone through the project and understood the photographs and the documentary record, we've kind of uncovered, as it were, the principles that the original pioneers followed, and we stick to those principles. So we don't allow ourselves to use, for example, circuit designs that date after 1947. So fortunately, the the Air Force published a good series of textbooks for aircraft electronics engineers, and that's a good set of references for what was known in radar and radio circuits and general electronics in the early 1940s. So I said we have an incomplete textual technical description and an outline of the logical design from the university archives. We have the original photographs and published papers. We have some collections of the pioneers who built the machine. Unfortunately, they're all no longer with us, but some of the material there is useful. Although we've also found that, you know, as they got older, they confused what was an Edsac 1 and Edsac 2. And so we've had to be a bit careful with recollections. And when we've been doing the project for about 4 years, we actually came across a cache of circuit diagrams. One of the engineers who worked on Edsac 2 came to the museum, saw our Edsac, and told us that he'd been an apprentice when Edsac 2 was just starting to be built. And one of his early jobs was to clear out a cupboard. And in that cupboard were a lot of diagrams of Edsac 1. But he'd taken them home to study them. Although he'd never actually got round to studying them. They were up at his attic. So he gave us those. And they were quite helpful because they did confirm a number of the things that we'd had to guess. Although they were diagrams of Edsac at the end of its life when there'd been a lot of evolution. But again, although the circuit diagrams differed from the early photographs, they kind of confirmed to us areas of the machine that we thought were a bit weak, that needed to be improved, because we found the obvious improvements in the later circuit diagrams. So how did we make the racks and chassis? That was fairly easy. Off the photographs, we could establish the dimensions, and we went to a local engineering firm in Cambridge and got them to make the metalwork for us. Oops, I went too fast. There was one challenge there. The wartime metal that was used to build the original Edsac, mild steel was much softer, and it was clearly all handmade on pan and folding machines and so forth. Modern steel actually is much harder, and we had some challenges in getting it to fold to some of the same sharp bends. But with modern CNC machinery, we solved problems like that by milling a little bit out on the reverse of the turn to make it more flexible. So again, a number of dodges to maintain the correct physical size, but work with modern materials. The next step we took was to reconstruct and prove the logical design. The diagrams we had were incomplete and inconsistent, and we knew they were written at an early stage of commissioning the original, and there were big gaps. So we essentially designed our own logic simulator and coded up the diagrams and the notes that we had and ran that through our simulator. So these are some of the kind of diagrams that we would get. They would tell us what some of the functional units were in the machine. And quite often those functional units would correspond to a chassis. And we could identify the chassis by the pattern of valves on it and so forth. And these diagrams told us how data flowed around the machine. And there were also some diagrams that told us what the typical delays were as information passed through the machine. So given that, we constructed our logical simulation written by one of our volunteers, a guy called Bill Purvis. And with that, we could run the simulations. And the logical simulator was capable of running original programs and producing the correct results, which was all very pleasing, although all very slowly. And although the simulator was hand-built for our own purposes, we extended it to output Verilog, and the output Verilog has been compiled and run on a FPGA. So we do have a silicon Edsac as well. And of course, it runs much, much faster than the original. And that's been quite useful to explore one or two design decisions. So the next question was, how do we map the logical design to the chassis? Well, fortunately, we have photographs of the machine under construction, which gives us more visibility, particularly of things in the middle and the rear racks. And if we look at some of those images, you can see there are little labels on them. And those probably tell you what the chassis is. And so the question in our minds was, could we amplify the images? Whoops, sorry, I've gone too far. Could we blow up those images and get to read the labels? I've lost the blown up image. The answer is no, we couldn't. The kind of granularity you can see on this photograph, these were photographs taken on glass plates, and you're actually seeing the granularity of the silver nitrate coating. With a bit of care and some knowledge, you can guess what some of the labels are. I happen to know that this particular chassis is a coincidence unit, and I can kind of surmise that the top line does indeed say coincidence, and the next line says unit, but which number unit and which chassis number to the right is impossible to read. So that didn't help us terribly much. This is what the original chassis looked like. So to fill out the story, we just basically had to look at the photographs, think how we would populate the chassis to achieve the effects, and then look for chassis on the photograph that seemed to have the same number of the different valve types that we use. And it was kind of like doing a jigsaw. Locating the first few pieces is really hard. Once you've got quite a lot of it nailed down, then it's merely a process of filling in the gaps. So this is what the original chassis looked like. And you'll remember that components, particularly capacitors, were quite big in those days. You'll see a number of inductances. Those are short delay lines used to retime some of the pulses. And then there were no printed circuit boards at that time. Everything was wired between tag strips and the valve holders. So it's a bit of a rat's nest underneath and a bit hard to unpick. So how did we acquire the parts we needed? Well, many but not all the valves are available commercially as new old stock. The valves used are EF54s and 55s. There's one EA50, there's some EB34s. Those are all widely used in radar, and radar systems are mostly procured by governments, and governments usually procure far more spares than they ever need, and those end up with the surplus dealers, and they're happy to sell them to us. We have a funny conversation because they often say, we've been waiting for someone to want to buy those, and they quote an expensive price, and we say at that price we're not buying them. And then suddenly they're very glad to have a customer, and the price becomes much more reasonable. Indeed, with one dealer, we did a negotiation where they got a guided tour of the museum and gave us most of their stock. That was quite a nice deal. And things like the tag strips and the coils, those are all handmade. I did most of the mechanical work on the machine. I'm a computer scientist by background and a programmer, so I wasn't trusted with electronics, but they let me do mechanical stuff. And so this is what one of our chassis looks like in comparison. You can see physically the metalwork is the same, and we're working with tag strips, but modern components are so much smaller. They do look very sparse in comparison to the originals. But that also means it's a bit easier for us when we're debugging and commissioning to get in there and attach probes and fix things and so forth. So what were we going to do about the memory tanks? That was a big problem because it's risky and costly to use mercury. To build a full store would have been about £160,000 worth of mercury. And the mercury tanks in the original machine had a real problem with temperature stability. They put them in lined wooden boxes to try and even out the temperature, but even then, the machine had to be kind of retuned to the memory tanks at sort of hourly, 2-hourly intervals, and that's not really viable for an exhibit in a museum. The tubes and end plates had to be made with precision engineering tolerances, and that would have been challenging. Certainly not something I could achieve in my home workshop, and that would have been something to send out to manufacturer and quite expensive. So we chose to go with a slightly later technology of nickel delay lines, magnetodistrictive delay lines, Those were used in machines from the very early 50s. So we're not being too anachronistic. And to get ourselves going, while we worked out how to build nickel delay lines, we as a workaround used some semiconductor shift registers as interim delay lines for the Edsac machine registers. So this is one of our magneto-destructive delay lines. You can see the coil of wire, and the principle of these is there are two little fingers that are worked electromagnetically. They put, you can just about see one in the towards the bottom right of the picture. They put a twist on the wire, a torsional twist that travels through and is picked up at the opposite end, where it moves the fingers inside a coil to regenerate the electrical signal. So we've built short delay lines like this for the machine's registers, and long delay lines for the machine's memory. This was a big research project in its own right, identifying the right kind of metal to use for the delay line, understanding how to weld the fingers onto the delay line, how to deal with problems of echoes and attenuation and so forth. It turns out, whilst delay lines were widely used in the 1950s, indeed through into the 60s, the understanding of the engineering of them has been completely lost. And talking to a few people who were in the computer industry at that time, it seems like it was essentially a craft skill. And once you lost Fred, who knew how to do it, you could no longer make delay lines. And we weren't able to find Fred, but now we have a Peter, and we look after him to make sure that we continue to be able to build our delay lines. So the original Edsac team the project was conceived of by Wilkes, who in due course became Professor Wilkes, head of the mathematical lab and computer lab. Indeed, he was still the head when I joined the computer lab in 1975 as a research student. But most of the work was actually done by his chief engineer, a guy called Bill Rennick. We met Bill's wife. Bill sadly died in the 1970s. After working on Edsac, he went to work for Plessey. But we met his wife, a very elderly lady now, and she came to visit the machine as we were constructing it. And she had two observations. She explained that our Edsac didn't have enough dust on it, and it didn't smell right because you couldn't smell that kind of hot dust smell you used to get out of TV sets. And she also looked at me and gave me a big wink and said, you know, it was Bill's machine, really. He made it work. And I think from reading the logbooks, it's very clear that Bill and his team, and we see some of them there on the right, worked extremely hard. That's obviously a very posed picture. They're all wearing suits and everyone is tinkering with something. But it gives an idea of what it was like in the construction phase. This is my team at a similar phase. We're rather more casual in our dress. We're also, of course, posing here. And indeed, the oscilloscope in the center is a stage prop. We use modern oscilloscopes and test gear to help us. So, for example, at the moment, we're running test programs on the machine, but we don't have the system for loading programs commissioned yet. So we've got a little Arduino box that knows how the store works and will squirt a binary pattern into the store and start it circulating. And that can be a test program for us. We've got several logic analyzers that are monitoring what's going on in main control and so forth. And obviously a lot of use of oscilloscopes. If you look at the age profile of the team, what is interesting is many of them do not like modern digital scopes, though they do like to have the old-fashioned analog scopes. They understand that there's a definite age split of those of us who are a bit younger, who think digitally and want to capture scope traces and take them away and study, and the older set of people who want something very analog, please. So this is the timeline of the project. We started 12 years ago with a feasibility study and set up a charity and raised £250,000 from donors. 2 years of the feasibility study, which was essentially doing a lot of the forensic engineering research to start mapping out the circuits and completing the fundraising, building a team of volunteers. We have about 30 people in total on the volunteer roster, of whom about 10 are very active, and others contributed perhaps at earlier stages, but are now less involved. We started the detailed design of individual chassis and prototyping in 2013. So there were 3 years of research, and having prototyped a few chassis and checked out some of the parameters and issues. Serious construction started in 2014. And obviously, as we began the construction process, we're also in parallel commissioning, starting to connect things together. A little bit more fundraising went on in 2015. And by 2018, we were just starting to run some test programs. In the last few years, we've had several things against us. The museum chose to re-roof the gallery, which we occupy. And so that meant for 4 months, we couldn't get near the machine. That was 2018. It took us a while to get back to where we were. Of course, as you know, in 2019, 2020, and 2021, 2021, COVID came along, and that meant the museum was shut for extended periods. And indeed, many of the volunteers, being of an older age profile, were obviously quite cautious about coming in and working together. We did actually do some engineering sessions by Zoom, with a couple of engineers in the machine, keeping a distance from each other, and various experts on a Zoom call offering their advice and staring at camera shots of scopes and logic traces and so forth. When will we finish? Well, we're into 2022 now. I think it'd be a bit optimistic to think we'll be done by the end of this year, but I would hope by early next year, certainly we will. There's not a lot more to be added. In fact, the next slide talks about that. We've built and installed 139 of the 142 total chassis, and the others are under construction. They're the IO system. The clock system is completely working. It's been working for ages. The arithmetic system is in commissioning. It did work standalone on its own tester. It was actually built by a volunteer here in Cambridge in his shed, and then we moved it to the museum in Bletchley. It is in the advanced stage of commissioning. We're essentially checking out each of the arithmetic operations now to make sure they work correctly. The machine's registers internally are held in short delay lines. Those short delay lines are now themselves in commissioning. We're swapping out some of the silicon register delay lines that we built, so silicon shift register delay lines, and replacing those by nickel delay lines. The main store delay lines have been tested. We're not ready yet to start swapping those in. The whole memory system, the recirculation through the delay lines, the addressing system and coincidence system, which is obviously has to, if you want to read data out of the memory, you have to address the appropriate tank. So you have to break the address down from the address digits to strobe the appropriate tank. And you have to wait for the word you want to be the word that is emerging from the tank and copy it into the machine. And that's called the coincidence system. So essentially, the processor and arithmetic unit will hesitate until the memory makes data available to them, and then proceed in lockstep, bit by bit, as the memory sends them data. And again, that's why the hardware level, the memory is 18 bits. The programmer sees 17 bits. That gives main control and arithmetic a chance to set things up to process data once it starts flowing. And main control is also in commissioning. It is substantially complete. The only thing we haven't commissioned yet is the transfer unit and the ability to write results back into memory. But that's something that's being worked on. And I'm hoping that the crew who are in on Friday will tell me we might have that working by the end of the week. And then there's the I/O system, and that's still being built. We've built the devices. We've hooked those up to our FPGA Edsac and checked that they work. So I'm optimistic we should be able to connect those very easily. So that's a tour through the reconstruction project and some of the issues we faced. I'm happy to pause there and take questions and discussion. Thank you very much for your attention.
Thank you, Andrew. That was very interesting and very well presented. I'll hand over to Alan to field the questions. And again, apologies to everybody for the confusion over the start date. We always, at this end, assumed it was 6:30. Don't know where the change came from, but sorry that you were delayed in the start and frustrated. If you can type any questions into the Q&A button, please carry on doing that now, and I'll hand over to Alan to organise the questions and ask Andrew to answer them. Thank you.
Right. Thanks, Rob. Thanks, Andrew, as well. So first question, which build standard, in particular with regard to Edsac 1 and 2, are you working to at the moment, Andrew?
We're building Edsac 1.
Right. Pleased to hear that.
Edsac 2 is an interesting machine because a lot of important new concepts came along with it. It was the first bit slice machine. It was the first micro-programmed machine. So from that point of view, it is interesting. But as a computer compared to its contemporaries at the time, it's not particularly exciting as a computer. And nobody's heard of it. And I think the important thing about Edsac 1 is that it was one of the very earliest machines, and it was the first one that was practical. And we want, in the museum context, to be able also to demonstrate and talk about the whole software system that was developed for it. And indeed, we run a very successful schools program. We'd like to be in the position where schools can do a bit of playing around before they visit and write some programs from Edsac. And when they come along, we can punch out their paper tapes and run them so they can experience what it was like to program in 1950, 1951. So Edsac is the more significant milestone in the history of computing, although it really is a miniature version of what Van Neumann sketched out in the EDVAC. I should perhaps say the Americans didn't get EDVAC working until about 1953. They wanted to build a much bigger and faster machine. They had more technical challenges. They needed to get government funding, and that took a long time to come through, and a whole host of other problems. And so it was quite some time before they got to realize their design.
Thanks. A question which I was about to ask if nobody else had, but this one's from John and written as, what is the MTBF and how do you feel that compares with the original model?
So we know the original machine was quite unreliable for two reasons. Three reasons. We have the logbooks that tells us. There were resident engineers during the working day, and they were clearly pulled upon to fix things. And we know from one or two of the users that if you're producing results for publication, you would probably run your program a couple of times or even 3 times just to be absolutely sure that nothing had gone wrong. That said, people's recollection is they got about 30 to 40 hours working time out of the machine a week, at least 35 hours, so it's about as useful as a Frenchman. And that's quite good by the standards of the machines at the time. Now, in the context of our replica, it's a bit hard to say what's mean time between failure because we're still essentially fixing design faults. So quite often things not working are because we're discovering that maybe signals aren't quite as at the right levels, or they're a bit delayed and so forth. We certainly are watching valves die. And our biggest challenge there is the EF54s. The original Mullards work extremely well, and they're the oldest. Post-war, there are a lot of substitute valves made by putting miniature valves in the tin cans and on the bases of the larger valves. And a lot of the EF54s we're using as substitute EF54s, and they do tend to short circuit. And when they do, it's quite unpleasant because they can pass high voltages and currents through to the next stage of the circuits. They cook themselves inside the tin can, and they're protected by a kind of foam rubber, which makes an awful smell and pours obnoxious chemicals over us. So that's a bit of a concern. So in fact, one of my things I've been doing over the last couple of weeks is going around all the suppliers, making sure I have got the world's stock of original EF54s. But overall, I guess but the machine is probably running, if we say on average 2 days a week, and we're probably replacing 1 or 2 valves a month due to failures as opposed to design faults.
Thank you. Interesting question. What will the new Edsac be used for?
Oh, to keep the building warm, especially in winter. Pumps out 9 kilowatts. So we pride ourselves on keeping as many machines as we can running, so we can demonstrate to people what computing was like in the past. And you have to think, modern youngsters coming through, even families where parents are in their 20s and 30s, their experience is all the personal computer and the tablet and the mobile phone. The world of the mainframe and the mini computer, let alone these vintage machines, is completely unknown to them. And it puts in context just how technology has developed, and what some of the vision of the pioneers who built the early machines. So we want to run it. We want to show people what it was like to work on a machine of that kind. And as I think I said, for schools and so forth, use it to support doing practical programming. We run a BBC Micros classroom as part of the school experience. So they sit in a 1980s classroom on BBC Micros, learning how to write simple programs in BASIC. And it turns out that's a much easier environment to teach people how to use than a modern PC, because the BBC Micro was simpler and BBC BASIC was a good language. So I'm hoping with Edsac, we are going to essentially be teaching people assembly code programming, but it's very simple because it's a simple machine. It's nowhere near as complicated as an Intel or an ARM processor. And you can teach someone the basics in a few minutes if you're kind of getting them to fill in the gaps in an existing program.
Okay, another Peter, if you were going to do the project again, what would you decide to do differently?
So the thing which is hurting us now, which might have made us operate a bit differently, is we broke the overall project up into sub-projects. So one team worked on main control, one team worked on arithmetic, one team worked on clock and other subsystems. And that meant we were doing lots of things in parallel, which was good for getting the thing built. Remember, there's 142 odd chassis there to be constructed. And we thought we'd done a good job of talking to each other and agreeing standards and so forth. But it was clear as we plugged things together, there had been misunderstandings, let's put it like that. And there hadn't always been enough discussion or enough understanding of some of the sensitivities of one part of the machine to another. So it may be if we'd had much tighter coordination at that stage, commissioning might be going a little bit faster. Working with volunteers, it's a challenge to get people to turn up more than 1 day a week. Again, having 2 or 3 teams working helps, but then they've got to coordinate. So ideally what I'd like to have found was a team of 10 really rather knowledgeable electronics engineers who are willing to commit to working 8 hours a day, 5 days a week on the project. But that's kind of not very realistic.
Right, a completely different question from Don. What sort of solder have you been using?
I don't think I want to answer that question. A lot of people used old solder from their sheds because they have more confidence in it.
Oh, lovely. Here's a really interesting one from Steve. Do you know the genesis of the term software? Steve remembers first hearing it around 1970.
I don't, to be honest, but I was an undergraduate in 72, and software was certainly a well-established term by then. Wilkes and 2 other people, Wheeler and Gill, wrote a book on programming the Edsac, and they certainly did not use the word software, but they did choose to use the American spelling of program. Wilkes was a bit like that. If there is an American word for something, he would use it. He was what's the word I want? Americophile or something like that. So software, there was a NATO meeting on something called the software crisis in the mid-60s. And that's when software got to be sufficiently large that actually it took forever to get the bugs out of it, and one person couldn't write the entire program. And that's kind of when software engineering got invented. So I think it's probably an early 60s term, but I don't have a definitive reference.
Oh, thanks for that. There's a question here about turning the machine on and off. I think this is probably the one that's on many people's lips. Can you comment on that situation, please?
Yeah. And the same question arises with our Colossus machine, which is also a valve-based code-breaking machine. And the mythology has it you leave them on 24/7. Well, that's expensive. The other mythology, which clearly the first machines prove wrong, was if you got that number of valves, it's always going to be breaking. Well, that was the experience of 1930s radio. And if you look at a 1930s wireless, as they would have called it, if you look at a 1930s wireless set, when you turn it turns on the high tension and the heater current at the same time. And so there's quite a thermal and electrical shock, and that's not good for the valves. What we do for both Colossus and Edsac is we've built ourselves a very modern power supply, which brings up the heater current in 3 stages over the space of 3 minutes. And then we bring in the high tension. The machine runs at 250 volts DC for most of the electronics. We bring that up in 2 stages, also over a minute. So it's 5 minutes from a cold start to the machine running. If we're working on the machine, we're quite happy to drop the HT and leave the heater current on. If we're making minor changes or fixing valves or something, we'll certainly take the high tension off. And with that kind of controlled switching on and off, we don't think that thermal electrical shock is an issue for us. And from what we know, it looks like they had some sort of switching arrangements, not automated, for the original Edsac. We had some operating instructions that tell you to turn on heaters 1, wait a bit, turn on heaters 2, wait a bit. So I think that the experience was don't bang these things with the full heater current and the full HT in one go. Bring it up slowly.
Yeah. How did Leo differ from Edsac?
A lot more input output, basically, because it was doing data processing. They added some additional instructions to the repertoire to meet their needs. Edsac really wants to do numerical calculations. It hasn't got very much in the way of logical orders or character handling or whatever, whereas the Leo people did that. They also learnt, they also thought a lot about how to make the machine more reliable, and they certainly improved a lot of the circuit designs for their machine. So they essentially kept the logical structure, improved the electronics where they could, and added some extensions to meet their particular requirement. And in the later life of Leo, they added magnetic tapes. I think they added a card reader. They added a zero graphic printer, all kinds of things. That might have been on Leo 2 or 3. I can't remember the exact history.
So what was it, the same delay lines for the memory?
Yep, same delay line concept. Again, they certainly made some improvements in the recirculation system. There's a paper by John Pinkerton on using automatic gain control to improve things. And they certainly improved some of the construction, because they went out to get things constructed by industrial suppliers, whereas most of the stuff on Edsac was built in-house by the maths lab technicians.
One or two questions around aspects of timing, which I know you've touched on, but one particular question, which perhaps may indicate a misunderstanding, is did the programmer have to take account of the timing of when words came out of store?
No, and in fact, this was a hot topic in the late 1940s. Alan Turing designed a machine called the ACE, and National Physics Lab built it, a version of it called the Pilot ACE, and English Electric productized it as a machine called JUICE. In that machine, you did have to understand the timing very carefully. And that meant you could write very fast programs, but if you changed anything in your program, it would all fall horribly apart. And Turing felt that was the right approach. You should squeeze the maximum amount of juice you can out of your computer. And that probably comes from his wartime code breaking experience, where the code breakers were up against it to crack codes within 24 hours. Von Neumann had the different view, and Wilkes absolutely endorsed it. And Wilkes and Turing had stand-up fights about this topic, that the programmer shouldn't have to worry about these things. So you just wrote your program, and if it was the case that the data you wanted had just gone back in the delay line, well, Edsac would look after waiting for you to find it. And I guess, if you wanted to, you could kind of think about optimal programming, but I don't think you'd get very far in Edsac, because basically the instructions have got to follow each other. So your data, fetching and writing data, is going to interrupt the instruction flow, and you've got no control over that. No, it was all about convenience of writing programs. They realized that if people could write programs quickly, they'd come on the machine, get their answers and go away, so they could do more work for more people. Whereas if people had to really think about and tune their programs, they'd be on the machine forever, and they'd have less people throughput, although they might have higher computing throughput.
I'm going to jump in now with a question of my own, which is, what was it that happened at the end of the 10-ish years when the machine came to an end? In particular, was there a lot of sort of legacy software that people were struggling with?
No, because with those early machines, because the next machines were typically so different and such a step forwards, people were happy to throw away their old software and start again, and get past the limitations of the machine. So as far as I know, I can't point at a reference, as far as I know, no one, for example, wrote an Edsac 1 emulator to run Edsac 1 programs on Edsac 2. Now, what certainly was done was a lot of the library routines were onto Edsac. So it wasn't a software at that stage, because we didn't have discs and tapes as huge storage media. All this stuff was on paper tape. Yeah. So no, again, it was in the 1960s where people suddenly got fed up having to rewrite stuff because stuff had got bigger. That was all part of the software crisis. And so that's where ideas about portability of languages across machines started to become important to get past that problem. But the manufacturers didn't like it because they liked locking their users into their machines.
Okay, thanks. We've covered most of the questions asked. There are one or two around software. What I think is that it would be nice to have a talk with you offline to see if a follow-up lecture could be done, which gets much more onto the software programming side.
Yeah, I've got a software talk. In fact, I gave it last night.
Right.
So we can do that for you on a future occasion. And if people want to peek, a bit of self-advertising, if you go to the National Museum of Computing website, we do put all our talks up there. There is a nominal fee, as you could imagine. We're struggling with getting visitors in the current climate, so we are putting some of our things online. People are very welcome to download and watch the talk there. The talk I gave last night is a tutorial on how to program Edsac and points you towards various simulators that you can use and example programs and so forth. But I also have a general talk on programming for an audience like this, so take a pick.
Okay, probably go for both, I think.
Okay.
Well, thanks very much for that. We're going to finish now, but just one or two people asked questions about recordings. So just to assure you that this is being recorded, and the recording, email the IET if you don't receive an email telling you how to get hold of it. So thanks very much, everybody, and thanks, Andrew.
Okay, my pleasure. I hope everyone's enjoyed the evening.
Good night.
Thank you, everybody, and good night.